Raith company is a leading precision technology provider. We have Raith staff and partners around the world who are supporting Raith instruments. These instruments are often used in nanofabrication and nanoengineering. We have a wide variety of dedicated electron beam lithography and multi-technique electron beam lithography instruments. We also have focused ion beam and scanning electron microscopy instruments. And during today's presentation, I will be focusing exclusively on the CHIPSCANNER scanning electron microscope for large area imaging. First, however, I would like to explain the link between the CHIPSCANNER and our electron beam lithography instruments. The story begins with Professor Richard Feynman of Caltech, who gave a speech in 1959 entitled "There's Plenty of Room at the Bottom." In this speech, he suggested that it would be possible to write the entire 24 volumes of the Encyclopedia Britannica on the head of a pin. He even suggested methods for achieving this goal, reversing the lenses of the electron microscope, or taking a source of ions and focusing them down to a very small spot. And Richard Feynman offered a prize to the first team who would meet this challenge, $1,000 of his personal money. 25 years later, at Stanford University, Tom Newman and Fabian Pease met this challenge by using electron beam lithography to write the opening page of Dickens's A Tale of Two Cities. These letters were written at a 25 nanometer line width within a 6 micron square, and this met Richard Feynman's challenge. And Richard Feynman mailed a check to Stanford University and left this world a few short years later. Since Richard Feynman's challenge, there have been decades of electron beam lithography advancements. And in fact, Raith is a world leader for electron beam lithography systems, basically reversing the lenses of the electron microscope in order to enable breakthroughs in nanoscale science and engineering. So in Raith's own history, we have decades of advancements in technology for electron beam lithography. Raith's roots start at Cambridge Instruments and also Philips. And in 1966 and the early 70s, the first electron beam lithography systems were offered commercially by Cambridge Instruments and also by Philips. Since then, there have been many decades of advancements in electron beam lithography technology. The instruments have gotten more and more accurate, have achieved higher resolutions, covered larger areas, gotten more automated, gotten more reliable, and have gotten faster. And nowadays, Raith is currently manufacturing models, several different models of electron beam lithography instruments, including the EPBG and Voyager systems that are shown here. So, we can reverse the lenses of an electron beam lithography tool. Now, why would we go back and do that? This electron beam lithography tool is the E-line system from Raith. It's a very popular model. It has an SEM mounted over a laser interferometer stage and patterning technology. And this is a very popular top-selling electron beam lithography tool. Now, why would we reverse the lenses of an electron beam lithography tool? Lithography, by definition, is the transfer of information into a material. And essentially, we're going to be reversing lithography. And I'll tell you why in a moment. In lithography, a CAD file is read in by the electron beam lithography instrument. The electron beam is patterned into a resist. The resist is developed and the pattern appears in the resist. And then the pattern is transferred into the substrate below. And lithography, that's just one step that I described. This loop is repeated over and over again, and a device is built up layer by layer. And these layers must be very carefully aligned to one another to properly build up the devices at the nanometer scale. And so that is lithography. If we reverse lithography, what do we have? We have what we call reverse engineering. And this is a very important application that Raith has been serving over the last 15 years. If you have an unknown device and you want to extract a design from that device, this is reverse engineering. And this is collecting information from a material. So an unknown device is deprocessed layer by layer, and each layer is imaged over large areas with a scanning electron microscope to resolve the very small features in these devices. Each layer can span a large area of about 1 centimeter squared. One layer must be very accurately aligned to the next layer in order to properly extract the design from the device. So over the past 15 years, the reverse engineering scanning electron microscopy has been an enabler for applications such as intellectual property infringement, design verification for hardware cybersecurity, and also design obsolescence, design recovery for hardware obsolescence. So, by reversing the lenses of an electron beam lithography tool, we therefore have what we call the chip scanner. And this chip scanner is a scanning electron microscope that can image areas over centimeter squared areas with nanometer resolution. The images can be stitched together with very high accuracy, and the images can be stacked layer by layer to a very high accuracy as well, and we call that 3D stitching. And so the chip scanner has been serving our clients in reverse engineering for the last 15 years. This is the CHIPSCANNER 100 model. It's an open architecture that can accommodate many different options, including 4 nanomanipulators for in-situ nanoprobing. There are other models of the chip scanner, like the CHIPSCANNER 150, which is shown here. The CHIPSCANNER 150 features an environmental enclosure with very tight temperature control, and temperature variation can cause stitching errors. So the CHIPSCANNER 150 really has the most robust and advanced stitching specifications among our chip scanner instruments. So the chip scanner is, in summary, a high-resolution scanning electron microscope that brings the advantages of decades of advancements in electron beam lithography instrumentation to scanning electron microscopy. It has special advantages over traditional scanning electron microscopes, those advantages being stitching accuracy, automation, and also speed. So let's have a look at the essential ingredients of the chip scanner. I mentioned the automation. large area imaging takes a lot of time, just like electron beam lithography. And it is required that these instruments reliably run unattended overnight, even over a few days, capturing these images over large areas. The laser interferometer is a critical ingredient to the chip scanner. This is a high precision stage that can measure the sample position down to 1 nanometer. It uses these beams of these laser beams that are incident on a very carefully manufactured mirror. The reflected beams go back and are interfered with a reference beam, and this is a way to measure the plane of the sample with very high accuracy and precision down to 1 nanometer. We also have, the chip scanner has a state-of-the-art scanning electron microscope column that can be varied, and the primary beam can be varied in energy, just like any traditional scanning electron microscope. Also, myriad electron detectors like the Everhart Thornley detector, the post-lens angular selective backscatter detector, and also in-lens secondary and backscatter electron detectors are all possible with the chip scanner. Finally, we have height sensing apparatus. So when you are imaging over large areas, it is important to keep the sample in focus. And this is a common problem for electron beam lithography. So that's why the chip scanner has built-in laser height sensing apparatus. And this allows the chip scanner to keep the sample in focus over large areas. Okay. So having a closer look now at the laser interferometer stage, here we have a 300,000x magnification image video being recorded here that shows a tin on carbon sample. This tin ball is being moved to the right by the user depressing the joystick on the chip scanner. And essentially, what you can see here is very precise and stable motion underneath the field of view of the scanning electron microscope. And anybody who is used to operating scanning electron microscopes always find that when you press the joystick at this magnification, this feature would be lost, completely lost, and would never be found again. But with the laser interferometer stage, this feature is just slowly moved to the right. And this capability allows us to map out the errors in the field of view. And so let me talk about the errors on traditional electron microscopes. Traditional electron microscopes all have fields of view with distortions, and that's signified by these non-square fields of view. These distortions come from imperfections in the electron optics. They come from nonlinearities in the scan electronics. So this is just a commonality among scanning electron microscopes. Also, mechanical stages for scanning electron microscopes are not really any more accurate than a few microns. And therefore, it's not possible to move the stage and stitch together these fields of view. So what ends up happening is, unless you have large enough overlaps, you can end up missing certain areas of the sample. So large overlaps would be required, okay, for imaging with a traditional electron microscope. And software would be required to fix these stitching errors. However, when you're dealing with thousands of images, software becomes untenable for correcting the errors in these images. A powerful desktop computer cannot correct for more than a few thousands or tens of thousands of images. Beyond that, the problem becomes untenable. But more importantly, is that software corrections themselves introduce additional errors inside the field of view as the software is trying to match up the edges of these images. And that makes 3D stitching impossible with software corrections. At least impossible according to the accuracy that is demanded by these applications. So, with the chip scanner, we have a calibrated field of view. The laser interferometer stage is used to calibrate the field of view, making it highly, mapping out all of the distortions, measuring and mapping out all of the distortions. And then this accurate field of view can be stepped with a very accurate laser interferometer stage, and these images can be stitched together. Also, the overlaps between the images can be minimized, and this really improves the overall speed of the chip scanner compared to a traditional scanning electron microscope.